Ideal gases are simplified models of real gases that are governed by two main assumptions. The first is that there are no interactions between the molecules due to low pressure in the system. The second is that molecular volume is infinitesimally small, essentially zero. See here in this example that M&Ms don't interact with each other and have no significant molecular volume. For cases like this, we use the equation PV equals nRT.
This seems pretty simple. Why can't we always use the ideal gas equation?
This works generally, but in high-pressure cases, the ideal gas model doesn't hold up. In reality, molecules of a gas have volume and interact with each other through attractions and repulsions. These billiard balls are like gas molecules at high temperature and pressure. The balls have a finite volume and bump into each other.
But wouldn't that mean our original equation wouldn't hold?
Good point. There are many equations of state that introduce new variables to account for these factors. One of them is the van der Waals equation of state. Let's look at how van der Waals deals with these intermolecular interactions and molecular volume. Let's start with intermolecular interaction. In real gases, the molecular interactions cause the pressure exerted on the container holding the gas to be less than the ideal case. This interaction term reduces the pressure and is proportional to 1 over v squared. We can use a new constant for this. Let's call it A. Now, when we plug in pressure into our gas equation, we use this updated form. Now we can account for the fact that molecules do have volume. When we allow our pressure to tend to infinity in the original ideal gas equation, our volume tends to zero. This makes no sense. For a real gas, all we have to do is introduce a new second variable, B, the molecular volume. Then we subtract B from V so that as P goes to infinity, the volume term goes to B. And now we have an updated form for V in our gas equation. Now let's put it all together. When you sub in our new expressions for P and V, then rearrange for P, this is what you get.
The values of A and B, do I need to memorize them?
They're actually unique for each gas and can be found in tables online.
Cool, now I can do calculations at high pressures and low pressures.